Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing our investigation into section 4.2, which was our introduction into the next big concept of our class, which is a vector space. In the previous video, we sort of discussed what things you need to define to even begin investigating a vector space. We saw that that included a set of objects that we call the vectors, a field of scalars, which for our class is going to be either exclusively the real numbers or occasionally the complex numbers, and of course two operations, a addition operation, a vector addition operation, and a scalar multiplication operation. Remember, we also briefly introduced that just in case we have a non-standard vector addition operation or non-standard scalar multiplication operation, we might use the notation of sort of a circle plus and a circle dot to indicate that that is our vector addition and that is our scalar multiplication that we've defined, if in case that is different than what is standardly done. Remember that after you've given that set of vectors, that field of scalars, and those two operations, then for something to actually be a vector space, it must satisfy 10 properties. And those 10 properties we sort of discussed and went over in the previous video. Those 10 properties are again listed right here. Remember really quickly what those were is that we had to have closure under both the vector addition and scalar multiplication operations. We had to have several properties that related to addition, which were these here, namely that addition, vector addition had to be commutative, associative, there had to be a zero vector, and there had to be additive inverses. Then there were a couple properties that specifically dealt with that scalar multiplication. The first was that the 1 actually has to act like 1 under scalar multiplication. You could call that the unit property. And that scalar multiplication would be associative as well. Then finally, the last two properties, 9 and 10 in the book and our sort of listing here, are distributive properties. There's two sort of distributive properties that you need. One is that scalar multiplication distributes over vector addition, and then also that scalar addition, so adding two scalars, distributes over scalar multiplication. So in the last video, we sort of went through, talked about these, talked a little bit about the notation. Now we're ready to actually get into an example of showing something is a vector space. So our big goal in this video is we're going to look at going through and formally defining a vector space. So that means formally defining the vectors, the field of scalars, and the operations, and then confirming these 10 properties. Then, after we do that example, we'll look at a couple what would be considered non-examples, meaning that these are going to be things that while we define the vectors and the operation in the field, they don't necessarily satisfy all 10 properties. So we'll take a little bit of a look at that as well to sort of see things that would not satisfy the definition of a vector space. Okay, so let's get right into it then. So for our first example, we're going to show that the polynomials of degree 3 or less with the standard operations of polynomial addition and scalar multiplication is a real vector space. So let's go through about this as formally as we can here. For this first example, you'll notice that we're just going to be using standard operations. In a later video, we'll actually do an example with some non-standard operations. But for right now, we just want to get a sense of what all this stuff really means. So we're going to keep it pretty simple and we're going to have the standard operations. But we'll still be pretty thorough with our notation here. So let's start with the vectors v, right? What are we actually treating as vectors here? Well, the vectors in this situation are actually these polynomials of degree 3 or less. So they're going to be everything that can be written in the form ax cubed plus bx squared plus cx plus d. Right? That would be sort of a general element of our vectors, right? Every vector is going to look something like that, where a, b, c, and d can be any number we like, and that would guarantee that we have a degree 3 or less polynomial. What field are we going to be using here? Well, according to this, we want to show that it's a real vector space. So our field of scalars is going to be the real numbers. Before we go ahead and talk about the operations, let's just define a couple vectors so that we can give a sort of general description of the addition. Let's just go ahead and let's let vector u be a1 x cubed plus b1 x squared plus c1x plus d1. We'll do v equals a2 x cubed plus b2 x squared plus c2x plus d2. And I guess w, because some of the properties do require 3 vectors, with our notation be a3x3 plus b3x squared plus c3x plus d3. The only reason I'm defining these ahead of time is that we'll need them when we start to get into the properties, and also to write out the operations, I need to at least have defined a couple vectors. All right, standard operations of polynomial addition. So this would mean that in our vector space, if we do u plus v, again, remember, we're sort of using this vector notation with the arrow over the letter. We could also use our old vector notation of the bold letters, but that's sort of hard to write by hand, easy to type out, harder to write by hand. So it's just, since we're being very careful right now about remembering what is a vector here, we are going to use that sort of arrow notation. Bold notation, though, would be fine as well. And I think your book sometimes does use that. So in this case, since we're doing standard polynomial addition, how would you standardly add these polynomials? Well, we know that when you add polynomials, you add the like terms. So we know the definition in general would be that we would get a1 plus a2 x cubed plus b1 plus b2 x squared plus c1 plus c2 x plus d1 plus d2. That's our definition of the vector addition. And then our scalar multiplication, if k is a scalar, then k dot u, again, doesn't matter we use u, but that's the one I wrote first. Well, how do you multiply a scalar onto a polynomial? We know it just distributes onto each term. So I guess it would become ka1x cubed plus kb1x squared plus kc1x plus kd1. Okay, so this right here, this doesn't confirm that it's a vector space. This is actually just formally writing out everything that needs to be stated to even start to define a vector space. What are the vectors? What is the field? What does the vector addition look like? And what does the scalar multiplication look like? And of course, along the way, I just let u, v, and w be some general vectors here. All right, now we need to prove those 10 properties. So to prove v is a real vector space, need to show P1 through P10 hold. So we're going to go through and do that, and we're going to talk about each one. So it's going to be a pretty lengthy exercise here because we've got 10 properties to do. So what is P1? Well, if we go back and we check, P1 is saying that if, no matter what two vectors we choose, that if we add them, it remains in the vector space. This is what we often reference as closure under addition. So we want to show closure under vector addition here. So how do we do that? Well, we would start by setting let u and v be elements of our vector space. So we've already sort of done that. We could probably skip that, and probably in future properties I will skip that because we've already sort of taken the time to define it here. What do we need to show, though? Well, we need to show that u plus v is an element of v. Okay, well, how do we do that? Well, according to our definition, u plus v is a1 plus a2x cubed plus b1 plus b2 x plus c1 plus this is x squared, x plus d1 plus d2. That's what the vector addition is. Now, how do we show that this is an element of v? Well, to be an element of v, you need to be a degree 3 or less polynomial. If we wanted to, we could probably just say that. We could say, well, this is clearly a degree 3 or less polynomial. If you wanted to be a little bit more, I guess, notationally clever, you could say, okay, let's go ahead and redefine each of these to be a new constant. So let's just call this a prime, b prime, c prime, d prime, just letting those be new names for the constants. Then this is clearly a prime x cubed plus b prime x squared plus c prime x plus d prime. And clearly, this is a degree 3 or less polynomial. So u plus v is definitely an element of our vector space. So we've proven our first property. Again, remember our vector space is all the degree 3 or less polynomials, so all we've really proven there is something you guys already know, which is that if you add two polynomials that are degree 3 or less, the result will also be degree 3 or less. Okay, let's go ahead and give ourselves a new page. We got to do a similar thing. So now we need to go ahead and do property 2, which is closure under that scalar multiplication. So we're going to let, this time, just u be an element of our vector space. So we need to show that k dot u is also an element of our vector space. So we do this very similarly. K dot u, we know by definition that's going to be k a1 x cubed plus k a2 x squared plus k a3, oh no, we did it in b's, sorry about that, kb1 x squared plus kc1x plus kd1. Okay, I guess we can go ahead and just redefine each of these again. We can just call them something new here. So I guess we could maybe call that, alpha, this beta, let's just use our same thing. It doesn't matter. A prime, B prime, C prime. It's obviously not the same A prime, B prime, C prime, D prime as the previous one, but the point is they're all just constants again. So this, of course, then equals A prime x cubed plus B prime x squared plus C prime x plus D prime. This is a polynomial of degree 3 or less. So k is an element of V. To be honest, like I said, you could probably just skip this and just say right from here, anybody, who's taken some algebra would know immediately that this thing is a polynomial of degree 3 or less, so that would probably be sufficient. But if it has a more specific form, right, if there was some other sort of format to our polynomial that we needed, doing the little trick of sort of redefining the constants might make it a little bit easier for somebody to realize, oh, this k doesn't really do anything, these are just constants times each power of x, so it's still a polynomial of degree 3 or less. All right, so we've shown both the closure properties. In other words, what we've basically done here is we've shown that whenever we use our vector addition or our scalar multiplication, if we start with something in our vector space, we will get something that is in our vector space. So in other words, we won't somehow end up outside of the vector space. Now we need to start confirming that the properties that we have actually act the way that we want for the operations, meaning that addition acts like we expect addition to act, and multiplication sort of works like we expect scalar multiplication to work. So P3, P3, P4, P5, P6, these all sort of focus on the addition operations. So if we go back and just take a look, P3 is going to be about commutativity, P4 is associativity, P5 is going to be the zero vector, and P6 is going to be the additive inverse. So let's go ahead and see how we're going to do each of those. So for P3, this would be plus is commutative. You don't have to write, obviously, the names when you're doing this, but just reminding what you're doing. What we need to do is we're going to let, again, u and v be elements of v. Probably could skip this because we already defined them at the beginning, but again, I'm just trying to be very, very thorough since it's our first example. What we need to show then is we need to show that u plus v is the same as v plus u when using our vector addition operation. So we could do this either way that you prefer. Since this is proving an equality, you could write out the left-hand side, you could write out the right-hand side, and work your way down in both, and then try to see if they're the same. Or if you prefer, you can start from the left-hand side and work your way to the right-hand side. It doesn't matter which approach. I generally, just because it is a more condensed version, will do the approach starting from the left-hand side and working to the right-hand side. If you don't like that approach or you find it a little confusing, feel free, obviously, to use that left-hand side, right-hand side approach. So we will go ahead, though, and just make a series of equalities. We know that u plus v, by definition, we said is a1 plus a2 x cubed plus b1 plus b2 x squared plus c1 plus c2 x plus d1 plus d2. That was our definition for how we add two of our vectors, or in this case, just add two polynomials. Now, keep in mind that all of these additions in here, you will notice notationally, I don't put a circle around them because these are just additions of scalars, right? A1, A2, B1, B2, C1, C2, D1, D2. All of those are just scalar values. Now, of course, we know that normal addition, adding numbers, is commutative. So I can certainly write this as A2 plus A1 x cubed plus B2 plus B1 x squared plus C2 plus C1 x plus D2 plus D1. That is certainly allowed, right? Because normal addition is commutative. And this, of course, is the definition of V plus U. Because if we look back, remember, V is the one that has all the subscript of 2. U is the one that has all the subscripts of 1. So if we think about the addition in this order, that's just V plus U. And that's exactly what we wanted to show. So we've now shown that our addition operation is commutative. All right. Now we need to go ahead and show that it is associative. So we need to do P4, which is that plus is associative. All right. So to be associative, what we need to do is this one we do need all three of our vectors, so 3 generic vectors. And what we need to show is that it does not matter how you choose to group your additions. So we need to show that U plus V and then plus W is the same as doing U plus and then V plus W. Okay, so that's what we need to show. Once again, could do a left-hand side, right-hand side approach and show that they're equivalent, or you can do something more like what we did here and work from one side to the other. So let's go ahead and work from one side to the other. So we're going to take U plus V plus W. So by definition, we know what this is. This is going to be that A1 plus A2 x cubed, plus B1 plus B2 x squared plus C1 plus C2 x plus D1 plus D2. And then we have that added vector addition to this W. And remember, W is the same sort of polynomial except we just used all the subscripts of 3. So it's plus A3 x cubed plus B3 x squared plus C3x plus D3. Okay, now we have this addition of this under this vector addition, which we know you just add component wise. So this would become A1 plus A2 plus A3 x cubed plus B1 plus B2 plus B3 x squared plus C1 plus C2 plus C3 x plus D1 plus D2 plus D3. Now all we're going to do is, remember, we're trying to get here, so let's sort of group the last two together. So I'm just going to put some additional parentheses. I'm just going to sort of group those last two to constants together. Why am I safe in doing that? Well, obviously, again, this is just normal addition in here, and we already know that normal addition is associative. You can group it however you like. So we can then split this as A1x cubed plus B1x squared plus C1x plus D1, that vector, plus these guys as a separate vector. So that would be plus A2, let's see some parentheses, A2 plus A3 x cubed plus B2 plus B3 x squared plus C2 plus C3 x plus D2 plus D3. Okay, now we know this, by definition, is of course the vector U. So this is U plus, and this, of course, is the definition of adding V and W. And so this is V plus W. And there we go. So we've proven that one. So P4 is also, so the addition operation is associative. We've proven P4. Now, when people see this sort of proof here, they're always sort of thinking, did we really do much? And the answer is sort of yes, sort of no. We didn't do much because all we basically said is that when you add polynomials, you add the like terms individually, and inside of each like term, or for each like term, you just add like normal addition. So, of course, if normal addition is associative, so is adding polynomials. But this is just a sort of formal way of proving that. Now later on, when we have non-standard operations, doing this sort of work is going to be much more important because we won't just be able to rely on, oh, this acts like normal addition. But for right now, this is mostly just trying to get you used to the notation of writing this out. All right, let's give ourselves another page. And we've got property 5 now. Property 5 is the 0 vector. So we need to come up with a 0 vector. So there's basically two things in property 5 that you need to do. You need to state what you think the 0 vector is, making sure it's something that actually exists in your vector space, and then actually show that it acts like the 0 vector is supposed to. So what we're going to do is we're going to claim that the 0 vector in this case is the 0 polynomial. So in our case, we're going to claim that it's 0x cubed plus 0x squared plus 0x plus 0. And clearly, we know that this 0 vector is an element of our vector space, right? We're just thinking about the all zeros degree 3 polynomial, right? That has a 0 coefficient for all of those terms. Now, what we need to do is we need to show that this really acts like the 0 vector. So let's go back one step. Let's just to be consistent, let's let u be an element of v. So what we need to show is that u under this vector addition operation with 0 needs to come back as u. So in other words, we need to show it really acts as 0. So let's go ahead and do that. So u plus 0. Again, we're going to work left to right here. Well, by definition, that's going to be a1 plus 0 x cubed plus b1 plus 0 x squared plus c1 plus 0 x plus d1 plus 0, which of course is just a1x cubed plus b1x squared plus c1x plus d1, which is indeed vector u. So there we go. So using this, the sort of 0 polynomial is going to work as the 0 vector here. Perfect. Now we can go to property 6. Property 6 is basically having additive inverses. So we need to give a general formula for what the additive inverse of a vector is going to be. Well, we can sort of imagine what that is going to look like, right? If we negate the polynomial, we should get its additive inverse. So we're going to claim that negative u is simply going to be negative ax cubed minus b1x squared minus c1x minus d1. So very similar to how we did this here. For the additive inverse, you have to basically come up with what you think the inverse looks like, and then you have to actually show that it acts the way it's supposed to. So make a note here. Clearly, this is an element of our vector space. Right? Of course, this is still a degree 3 or less polynomial, so that's going to work. So we're going to let u be an element of v, and now we need to show that if we do u plus negative u, we get the 0 vector. In other words, that each element, any arbitrary element, has something that when you add to it, you get the 0 vector, which would be its additive inverse. So let's go ahead and show that. So according to our definition there, if we add that, well, we would get a1 plus negative a1 x cubed plus b1 plus negative b1 x squared plus c1 plus negative c1 x plus d1 plus negative d1. And then, of course, that is going to come out as 0x cubed plus 0x squared plus 0x plus 0, which we just found out in property 5 is what we count as the 0 vector. So there are additive inverses. Perfect. So at that point, we've confirmed all the operations that are all the properties that relate to that vector addition operation by itself. Now we need to turn to the scalar multiplication properties. So if we look back, we're going to focus on 7 and 8 now. 7 is the fact that the 1 really acts like 1. Sometimes this is referenced as the unit property. And 8 is that scalar multiplication is going to be associative. Oh, I'm sorry about that. I'm just spinning around. Too many properties, I guess, already. But let's go ahead and take a look at 7 and 8. So we'll go further down. There we go. Not quite there yet. We can probably fit property 7 here. So P7, this is often referenced as the unit property. So this one, we can just say let U be an element of our vector space, and we need to show that 1 dot U is equal to U. So in other words, when you use the scalar 1 and you use your scalar multiplication, you get the same vector. So again, we'll just work from the left-hand side to the right-hand side. 1 dot U, by definition, is going to be 1 times A1 x cubed plus 1 times B1 x squared plus 1 times C1 x plus 1 times D1. Keep in mind here, notice that these dots are not circled because this is just normal multiplication of real numbers. This, of course, is A1 x cubed plus B1 x squared plus C1 x plus D1, which, of course, is vector U. So we're all good there. So it does have the unit property. Okay, we can move on to our next one. P8, right? This is associativity of the scalar multiplication. So here we're going to let U be an element of V, and we need to show, I think we usually group them outside first. It doesn't matter, of course. But yeah, we're going to do K1 scalar multiplied with K1, or K2 scalar multiplied with U, and then show that you could multiply the scalars first. Okay, perfect. So let's go ahead. We need to show that K1 scalar multiplied with K2 scalar multiplied with U is supposed to be equivalent to K1 times K2 as a real number multiplication, and then scalar multiplied onto vector U. Once again, we can just start from the left-hand side and work our way over. So K1 scalar multiplied with K2 scalar multiplied with U. Well, we can figure out what happens in here first. That's going to be K1 scalar multiplied with K2. We know is going to distribute onto each piece. So I guess we're going to get parentheses K2 A1 x cubed plus K2 B1 x squared plus K2 C1 x plus K2 D1. And then we know that this scalar is going to just distribute onto each one. So this is going to be K1 K2 A1 x cubed plus K1 K2 B1 x squared plus K1 K2 C1 x plus K1 K2 D1. Okay, now we're going to do that sort of same trick. Let's just imagine sort of grabbing the K1 and K2 together, which of course we know because we know that normal multiplication of real numbers is always associative. You can group it however you like. And then we can think about that as K1, K2 scalar multiplied with A1 x cubed plus B1 x squared plus C1x plus D1. And of course, that is the definition of U right there. So K1, K2 scalar multiplied with vector U. Check. So we've gone ahead and shown that P8 it holds in this case. In other words, that scalar multiplication here is an associative operation. All right, last two, we've got our distributive properties. So both of these two properties are going to involve both our vector addition and scalar multiplication operations. First, we need to show that a scalar distributes over vector addition, and then we need to show that scalar addition distributes over scalar multiplication. So let's go ahead and start with property 9. So for property 9, we need to let U and V be elements of V. And what we need to show is that K dot U plus V is the same as K dot U plus K dot V. Once again, we'll just go sort of left-hand side to right-hand side. So K dot U plus V. We know that that's going to be K scalar multiplied with the U plus V, which is going to be A1 plus A2 x cubed plus b1 plus b2x squared plus c1 plus c2x plus d1 plus d2. Absolutely. Then we know that when we do the scalar multiplication, it distributes onto each thing. So we're going to get k a1 plus a2 x cubed plus k b1 plus b2 x squared plus k c1 plus c2 x plus k d1 plus k d2, and I'll just keep that in parentheses. Oh, I guess we're jumping ahead there, excuse me. So k and times d1 plus d2. All right, now let's go ahead and distribute our k onto each piece. So it looks like we would get ka1 plus ka2 x cubed plus kb1 plus kb2 x squared plus kc1 plus kc2x plus kd1 plus kd2. Okay, now what we can sort of imagine here is if we take this, this, and of course treat the other ones, then that should be clear that that's how we would do our vector addition, or if you prefer, how we would do polynomial addition. So this time I will actually write it out in those colors so you can sort of see that. So this should be ka1 x cubed plus kb1 x squared plus kc1x plus kd1. And then our vector addition, which just basically says add the polynomials, and then ka2 x cubed plus kb2 x squared plus kc2x plus kd2. Now, of course, this is the definition of that scalar k multiplied onto our first vector. So this right here is k dot u. And then we have our vector addition, and this, of course, is the definition of k multiplied onto our second vector. So this is k dot v. And there we go. We've shown that you can distribute the scalar multiplication over your vector addition here. So we've proven the first distributive property. All right, we have one last property to finish this up. We got to do property 10, which says that normal addition distributes over scalar multiplication. So for P10, we only need a single vector, so we're going to let u be an element of V. And we need to show that K1 plus K2 scalar multiplied with u is the same as K1 scalar multiplied with u plus K2 scalar multiplied with u. Now, always interesting on P10 here to recognize that this is just a normal plus here because this is just adding two numbers, but this plus, because both of these are vectors, must be the vector addition. This would be especially important to recognize the distinction here in later examples where this vector addition might not be the standard operation we're used to. All right, let's go ahead and actually show this then. So again, we'll work from the left-hand side and make our way to the right-hand side. So K1 plus K2 scalar multiplied onto u means that we distribute this onto every element of that u there. So that would be K1 plus K2 times A1 x cubed plus K1 plus K2 B1 x squared plus K1 plus K2 C1x plus K1 plus K2 D1. Now, this is just a normal multiplication, so we can go ahead and distribute that. We know that that's safe. So we get K1A1 plus K2A1 times x cubed plus K1B1 plus K2B1 x squared plus K1C1 plus K2C1 x plus K1D1 plus K2D1. Once again, we'll sort of do the same trick. Let's grab each of these and treat that as one polynomial, and then each of these and treat that as a second polynomial, and then use our definition of our vector addition here. So this would become K1A1 x cubed plus k1b1x squared plus k1c1x plus k1d1. That's all the blue stuff. And then that would be vector added to all the red stuff, k2a1x cubed plus k2b1x squared plus k2c1x plus k2d1. Then, of course, all of this is the definition of k1 distributed onto our polynomial. So this is k1 scalar multiplied with u plus, and this, of course, is the definition of k2 scalar multiplied on there. So that's k2 dot u. K looks very weird there, so let's just get rid of that. Let's just get rid of the whole thing and just rewrite it. This would be k2 scalar multiplied with u. And notice that is exactly what we wanted to show there. So there we go. So we've proven all 10 properties hold. What this means is since P1 through P10 all hold, the polynomials of degree 3 or less with standard operations is a real vector space. So we've just gone ahead and we've actually proven our first example, our first full example of an actual vector space. We've confirmed that all 10 properties hold. The polynomials of degree 3 or less will act as a real vector space. Now, like I said, in this one, there wasn't, most of the sort of difficulty, if you will, was due to the fact of just the sort of the notation, right? There's a lot of sort of unknowns and constants being used just to keep track of what these polynomials of degree 3 or less looked like. So there wasn't really much deep content to this because all the operations were standard operations, but it was more just helping us set up how the notation would look if we have to go through and deal with 10 properties like this. To wrap up this video, this is not going to be the only vector space we actually formally prove. We will see another one in the next video. In the next one we do, we'll have some non-standard operations. So it'll give us a chance to really think about how can we confirm these properties even if the addition and multiplication we're using isn't what we would typically expect. But before we do that, I'd like to look at a couple of non-examples. And what I mean by non-examples is we're going to look at some things where we have all the same definitions. So in other words, we're still given a vector space, we're still given a field, we're still given operations, but they don't necessarily satisfy all the properties. And I think that'll help you sort of really think about what these properties are sort of requiring. So let's really quickly look at a couple non-examples. So the first non-example that I'd like to look at is we're going to show that the polynomials of degree exactly 3, so notice that this is what makes this one a little bit different than what we just did. Now it says exactly 3, do not form a real vector space with the standard operations of polynomial addition and scalar multiplication. So this is basically the same as the previous example, but the big difference is that now the polynomials have to be degree exactly 3, whereas in our example it was 3 or less. Now, when you need to show that something is not a vector space, all that means is that you need to find a single counterexample to a single property. So one example where one property fails. As soon as one example of one property fails, then it automatically doesn't count as a vector space. So as always with mathematics, showing something is false or showing something is not following a definition or statement is much easier than proving that it is following that or does fit the definition, because like you saw in that proof we just did, we had to consider everything in complete generality. But since we're trying to show that it's not a real vector space, we just need to come up with a single example. So I'm going to start very simple here. Let's just think about property 1, closure under the vector addition. Well, considering it should be pretty clear that clearly x cubed is an element of v here, right? X cubed is definitely a polynomial of degree exactly 3. And negative x cubed plus x is also an element of v. That is definitely a polynomial of degree 3, because remember, degree is just whatever the highest power that's present. So this is degree 3, this is degree 3. But if we were to vector add those, x cubed, vector addition with negative x cubed plus x. Well, we know what would happen is that we'd be treating this one as 0x cubed plus 0x, this one would be treated as 1x cubed plus 0x squared plus 0x plus 0. And then we'd be vector adding that to minus 1x cubed plus 0x squared plus 1x plus 0. These, of course, would cancel, but we would end up with a 1x, right? Because we're just using standard polynomial addition. So this would be equal to x. But notice, x is a degree 1 polynomial. It is not degree exactly 3. So x would not be an element of v. So what we've just shown is we could add two things from our vector space and end up with something that's not in our vector space. So v is not closed under plus. And we're done. We found one example where we added two things and we ended up outside our vector space. That means it's not actually a vector space. It doesn't have closure under addition. Now, do other properties fail? Well, yeah, actually, if you want on your own, what you can do is this also fails property 2, property 5, and property 6. Why does it fail these as well? Well, remember property 2 is closure under scalar multiplication. You can try that with what happens when you multiply by a scalar of 0. When you multiply a polynomial that's exactly degree 3 by 0, you're going to end up with the 0 polynomial, which is degree 0, which isn't in your vector space. So it's going to fail there. Also, similarly, P5 is the one about the 0 vector, right? In this case, the 0 vector is not an element of V, because the 0 vector for polynomials is the 0 polynomial, but that's not degree 3, so that's not going to be in there. And of course, if there isn't a 0 vector, well, then this guy doesn't really work either, since P5 fails. So, all of these will also fail. Now you'll notice, though, that I don't mention P3, P4, P7, P8, P9, P10, because those will actually pass. All those properties still hold. And that should sort of make sense, because all those properties had to deal with the operation. And remember, the operations are still the standard operations that we just did in the previous example. So of course, those properties about the commutativity of vector addition or the associativity of scalar multiplication shouldn't fail. We didn't change any of that. What fails here are all the things that deal with the fact that we switched from degree less than or equal to 3 to exactly 3. So we lost closure. We lost closure under scalar multiplication, we lost the 0 vector, and we also lost additive inverses because we don't even have a 0 vector. So what that basically tells us is that this one would not be a vector space. Okay, let's go ahead and take a look at some other non-examples that involve non-standard operations. So for the next one, we have our vector space V that has elements AB, where A, B, and is an R. So in other words, they're two-dimensional vectors, or if you want, you can think about them as ordered pairs. And we're going to define the non-standard addition operation, where when you add them, A1, B1 plus A2, B2, you reverse their positions and add them. So you get B1 plus B2 and A1 plus A2. And you'll notice it's normal addition here, because that's just going to be adding the numbers, not the vectors. We're going to define scalar multiplication as normal, and we're going to show that this does not form a real vector space. I would strongly recommend, whenever you see a non-standard operation, just for your own benefit, give yourself a little example to make sure you understand how it really works. So just as a little example, this isn't my counter example, it's just making sure I understand how this addition operation works. Let's just make up some vectors. I don't know, how about we pick out 1, 2, and we add that to 3, 4. So what that would tell us to do is that B1 and B2, that would be the 2 and the 4. We're supposed to add those together first. So this would give us 6, and then we'd add the 1 and 3, but we'd put it in the second spot, and that would give us 4. Just to make sure we understand it. Okay. So why does this not form a real vector space? Well, if you want, you can check P1 and P2, the closure ones, but actually closure is going to work here. If I add to, ordered pairs even though I'm doing this sort of weird addition, it's still going to be an ordered pair, so it's still going to be in this vector space. Same thing with scalar multiplication. We didn't change scalar multiplication, it's just defined as normal, which means that it's like KA1B1 is KA1 comma KB1. So there's not going to be any issues with closure here. Instead, it's going to be with some of the other operations. So I'm going to actually show a counterexample to P4. What was P4? Remember, that was associativity of the addition. So in other words, I'm going to give a counterexample to the associativity of this new operation here. So to do that, let's go ahead and let's let U equal 1, 2. Going to keep these nice and simple. V equal 3, 5, and let's let W, the third one, because for associativity you need to define 3 vectors, equals 0, 4. So let's go ahead and look at U plus V, and then add W. So that would be adding these two first, which would mean that we would add the second components and put them first. So that would be 7, comma 4. And then we'd be adding that to 0, 4. And then that would mean, again, we'd take the second components, add them, and put it first. So it looks like we'd get 8, 7. Now let's see what happens if we add these two together first. So we're going to do U, and then we're going to add that to the result of V and W. Okay, so if we go ahead and do that, that's going to be U, which is 1, 2, plus, and now we need to add these two together. So we add these first, 5 and 4, that's going to be 9, and put it first. And then 3 and 0, that's going to be 3. Okay, now we add these guys first, that's going to be 5, and we put it first. So 5, and then 10. What do we notice? Well, these things are clearly not equal. So it matters if we group U and V and then do W, or if we do V and W and then add the U. So in other words, it's non-associative. So we've just shown it's not a vector space. Does that mean that that's the only property that fails? Well, no. If, again, on your own, you can check P5, the 0 vector, P6, the additive inverse, and P10, the distributivity of normal addition or scalar addition over scalar multiplication also fail. So all these fail as well. And if you want, you can try to show how each of those fail. Or if you prefer, just for some additional practice, come up with your own counterexample to P4, right? You can come up with another set of vectors, like instead of the ones I chose, and show that the order in which you add them really does make a difference. Now, just as a warning, just because also I think it's a little bit funny, when I was first doing this, I picked out, I believe, 1, 2, 3, 4, and 5, 6, and this actually worked, meaning that this way matched this one. Does that mean that P4 is proven if I do that? Of course not. Remember, when we give a counterexample, we're showing one single moment where the property doesn't work. That there might be other ones where the property does work. But the point is that for this to be a vector space, this property always has to hold. So even though it might hold in some situations, the fact that we showed one specific spot where it doesn't hold is enough to rule this out as a vector space. All right, let's take a look at one more, again with a non-standard operation. This time we gave a non-standard addition. Let's go ahead and see one with a non-standard multiplication. So we're going to consider the structure V. The vectors in this case are going to be 2 by 2 matrices. We're going to define the addition operation as standard, meaning that if we add A11, A12, A21, A22, and we add that to B11, B12, B21, B22, well, you're just going to do that as you would expect and get A11 plus B11, so on and so forth, right? You're just adding component-wise. But the scalar multiplication is different. Instead of just distributing the k onto each one, you distribute k squared onto the diagonal, and you don't do anything, and you just multiply a normal k onto the to the anti-diagonal. Now, this is a really interesting one. If you want, on your own, you can go through and show that P1 through P9 are all satisfied. So this meets the first 9 properties of being a vector space. But unfortunately, it fails property 10. So we're going to give a counterexample to P10. So to do that, we're going to let U be an element. You know what? I think I got a little bit ahead of myself because I like this example. But let's just go ahead and just give ourselves a quick example of this. So not my counterexample yet, but just an example to make sure we understand like this operation. So if we do 2 times, say, 1, 2, 0, 4, what that would end up being is we would square this and multiply it here. So we would get 4. We would multiply this normally and get 4, and then 0, and then we'd square this and multiply it here, so it'd be 16. So that's how that operation works. Okay, like I said, if you want, you can go through and you can actually confirm that this setup satisfies P1 through P9, but it fails P10. So here's my counterexample to P10. So I'm going to have my vector be equal to 1, 0, 2, 3. Again, always like to keep them pretty simple. And I'm going to have my K1 be equal to 1 and my K2 be equal to -1. So one way that we're supposed to look at it is K1 plus K2 scalar multiplied with U. So if we do it that way, K1 plus K2 is going to be 0 scalar multiplied with U. And of course, if we look, 0 squared and 0, it's going to just 0 out every element. So we're going to get 0, 0, 0, 0. Okay. The other way we're supposed to analyze it is K1 scalar multiplied with U. And then we're supposed to vector add that to K2 scalar multiplied with U. So since I'm doing K1, that would be 1. And since 1 squared is going to be 1, that's just going to be multiplying my matrix by 1. So I guess I'm going to get 1, 0, 2, 3. And then I'll have to do my vector addition with K2 times U. Now K2 is -1, so on the diagonal, I'm going to multiply by 1. So it looks like I will get 1 and 3. But on the anti-diagonal, or everything else, I'm going to multiply by -1. So it looks like I'll get 0 and -2. Now, of course, how do I actually do this addition? Well, we said to find the addition operation is standard, so just standard matrix addition. Looks like I would get 2, 0, 0, 6. Now, of course, you can see that these are not equal. So that tells me property 10, the fact that normal addition does not distribute over scalar multiplication, fails. We could maybe think of some examples, some scalars and some vectors where it does work, but we've seen at least one example where it fails. So this thing, despite satisfying every other property in complete generality, this is not a vector space. Okay, so at this point, we've proven something is a vector space, and we've seen several things that fail at least one property of being a vector space. In our next video, we'll go through and we'll do another proof, similar to the very first one, of confirming something is truly a vector space. But to make it a bit more interesting, we will have some non-standard operations to work with.